Yes, I'm Jo Van Herwegen, I'm professor at UCL, as Fliss already mentioned, and I'm the director for the Child Development and Learning Difficulties Lab. And in the lab, we focus on research that relates to raising educational outcomes for all children, but especially those with special educational needs. So we look really at a wide range of aspects within that, because of course we start with, looking at the child. Who do children learn? What does that mean in terms of their mind and their brain, but also in terms of how do they learn in terms of behavior? But then we also look at the wider context in which they learn. So then we're thinking about the parents, the schools, the teachers, their peers, and then also sometimes around what the wider public might think within that. So thinking about dominant beliefs or myths. You might have heard me talk about neuromyths already. So incorrect beliefs people might hold and how that might impact then on learning for children, especially those with special educational needs. And that then obviously relates also to policy making. So we've done research looking at, the EHCP process, for example, and other wider policies that might impact children's learning and raising educational outcomes for all children. So that's a little bit about myself and the lab and what the research we focus on. But a lot of that research focuses on how do we raise educational outcomes, and especially how do we raise mathematical abilities. And so before we can start to think about how do we raise mathematical abilities, we first might need to look at, where does it all go wrong? Why do some children struggle with maths and others do not? So talking a little bit about children with or students with special educational needs, I know I'm talking to a very educated audience, but I'll just whiz through this. So as you may know, a child in the UK is considered to have special educational needs if he or she has learning difficulties that require additional support outside of, good quality teaching. Okay. And in the UK, that's quite a large percentage of all children. So we mustn't forget that when we talk about children that need SEN support, we're talking about 12.6% of all children, or, over 1 million students. Now, today, the reason why I'm bringing up the different categories is because, of course, there is a little bit of a dispute around how do we talk about SCND. There are so many different terminologies and concepts used. So I'm going to probably move between the two. So we can look at this in terms of using the Centre Code of Practice and talking about the 4 categories of need. So talking about students who might have communication and interaction needs, students who have cognition and learning difficulties, those who have social, emotional, and mental health difficulties, and then those who have sensory and physical needs. And we've looked actually at all of those 4 groups when it comes to mathematical learning difficulties, or why certain students might have difficulties with maths. However, today, because this is a big question and there's lots of different groups we could look at, I'm going to focus on the most common types of needs. And if you look at the most common types of needs according to those 4 categories in the UK, then we know that, for example, the largest proportion of students that have an EHC plan are those on the autism spectrum. And so I'm going to talk a little bit about what we know about mathematical development in autism. And then the larger group that has general sense support in the UK are those with speech, language, and communication needs, or SLCN. And again, I'm going to talk a little bit about that. We've also done, and I'm going to also focus a little bit about cognition and learning difficulties, but won't have time to go into mathematical development in those with vision impairment, but I can answer some questions around that as well. I'm just going to move you. There you go. So why are we looking at mathematical development in these groups? Well, we do know that when it comes to students with SCND, there is a gap in terms of the educational outcomes between those with SCND and those without SCND. So a recent report by Sam Tuckett from the Education Policy Institute has looked at how many students he looked at the English and Maths GCSE outcomes in those with SEND and those without SEND. And what you can, I don't know if you can see my cursor on the screen. Can you see my cursor on the screen moving? So then you can see is on the left-hand side of the graph, we see the gaps in terms of months. with the darker green line being students within the statement or an EHCP. And then those with the lower here with the lighter green are those without an EHCP but still have SEND. And as you can see, there's quite a gap for some of these students in terms of their mathematical outcomes at GCSE levels. We also know that this gap has grown as a result of the COVID pandemic. I'm really sorry, my cat wants to be let out, so I'll just have to pause for 1 second.
How unprofessional is that?
I know, I'm really sorry, but otherwise the cat would be moaning so much. So, right, so when we talk about students with SEND and mathematical outcomes, if we look at the early years foundation stage profile, for example, we see that in 2021-2022, 19% of children with SEN achieved a good level of development, which was 6% lower than the figure from 18 to 19, which was 25 at the time. And if we look at, the key stage 1, the teacher assessment of the percent, and looking at the percentage of students that meet the expected standards, we see that that's consistently lower for those with SEN compared to those with no SEN. That's not just for mathematical outcomes, especially, when we compare it to writing, but we see that it's consistently across the board, across the number of years. So I hope, but I'm sure I didn't have to convince you, that you are now aware of the fact that there is a gap when it comes to mathematical outcomes for students with SEND, and that gap starts or is there already early onwards, so from the early years onwards. One of the difficulties we might need to keep in mind is the fact that maths, when we talk about maths, it's a multi-componential aspect, right? So there's many things that make up good math skills. So when we talk about maths, we can look at basic mathematical processes that are learned early onwards in the early years and even before that. So thinking of things as subitizing, and I'll come back, come back to you on how we assess subitizing. So subitizing is the ability to see how many items there are without the need to count. So I don't know if you can see my hand, but, so you don't have to count as 5 fingers. Most of you will know that if I show a hand, there's 5 fingers. So that's your subitizing ability. We also know that magnitude processing, what numbers mean, what are large numbers, small numbers, where is more, is important in terms of learning mathematical abilities, as well as its number line abilities. We know that these early or basic mathematical processes allow children then to develop other mathematical abilities, such as learning number facts, procedural skills such as addition and subtraction, and understanding concepts like zero, for example, or how a decimal system. And of these kind of abilities in green allow then children to do tasks in schools such as counting, word problem solving, computational counting, as well as other math-specific tasks. Altogether, these abilities in yellow, green, and blue allow us to measure a child's mathematical achievement. So that's kind of an overall term that is used to refer to all of these different aspects. So giving you a few examples. So for example, when we talk about magnitude processing, this is the understanding of, what are large and small numbers. Often we have a task that we call is an approximate number sense task, in which students or young people are presented with dots, blue and red ones of different sizes. And for a very short amount of time, they're shown these dots, and they then need to say which side had more or less. Okay, and we make that sometimes easy by having amounts that are far different from each other. For example, 8 versus 16 dots. And sometimes we make this harder by making the ratio smaller. So for example, having 8 versus 9 dots, for example, where it's very difficult to see that there is a difference without having the ability to count, because we present it in such a short amount of time that people can't use their counting abilities. For subitizing, we can kind of show people smaller amounts for as long as they have to, and we measure how long it takes them to respond to, for example, say that there are 5 dots or that there are 5 dots here. And as you can see, these dots are presented randomly, so it's difficult to kind of immediately see how many dots there are. But when we order the dots in a particular way, especially when we order them in kind of dice-like patterns, it's very easy to recognize immediately without counting how many dots there are. And then we have number line abilities, where we give children a number line. We start, of course, with 0 to 10, and then maybe look at 0 to 20, and then 0 to 100. And we say to children, look, here is a number line. 0 goes here. 10 or 20 or 100 goes here. Where do you think the number? And then we give them various numbers. And we ask them to place them on the line. And we can then measure how accurate they are in their placing of the numbers along that number line. So, why may children with SEN fail maths? I'm going to ask you this question and see if you can put anything in the chat in terms of why you think some children, especially those with SEN, might fail at maths. Anyone want to put some ideas in the chat? Thank you, Morel. Lack of confidence. Yes, so indeed, recall might be an issue. We'll look at that. We know indeed, yes, memory problems. That's a nice one, Emma. We know that there are indeed so factors like absence from school, confidence, they're all very important. The ability to think abstractly, I think that's a very good example. Right, so you've already mentioned a few of them, so let's look at why children may fail. So I already mentioned that mathematics is a multi-componential subject, and we've spoke about how children need to kind of learn how to do counting, use strategy, have conceptual understanding. So this relates to the idea that some of these aspects are quite abstract, and they need to have access to maths facts. So, you can learn the multiplication table, but, you might not be able to always retrieve that information as quickly as some people, as and when you need it, basically. Someone mentioned in the chat.
He thinks we're failed with you to share.
Sorry, there's someone who's got their microphone on, so we can hear everything. Might be useful to switch it off. People also, need numerical representations. So as we mentioned, these often refer to these kind of basic mathematical abilities. Some people refer to it as a number sense. You may have heard of this before. So this is your ability to know where where larger and smaller numbers go, your ability to estimate, your non-verbal numerical knowledge. Your ability to estimate is part of that number sense as well. And that's kind of one of those basic abilities that people need. But we mustn't forget that there's a lot of other, what we call domain general abilities that people need as well. And again, this was mentioned in the chat. So, you need good working memory or good memory. You need to be able to hold information in mind to manipulate that information, especially when you're solving simple additions, for example. We also know that mathematical abilities relate to visuospatial skills. So this is your ability to orientate yourself in space, but also know where objects are related to you and to other objects in space. And the reason why that is important is because if we think that numbers go along a number line, and we kind of know that the numbers that are small go on the left-hand side, especially if you read in English from left to right. So those numbers go on the left-hand side, and that larger numbers go on the right-hand side. If you have poor visuospatial abilities, then your number line will be structured differently, and you'll probably have a different sense of what are larger and smaller numbers or where numbers go. So there is research to suggest that visuospatial skills matter as well. We also know that how fast you can process information relates to mathematical abilities, but also your ability to inhibit information. So when I'm asking you to take 4 and to add 5, what you have to do is inhibit all other numbers that are not relevant to it. So we're not talking about number 3, we're not talking about number 7, we're talking about number 4 and 5. So you have to inhibit. You also have to inhibit your information when you kind of switch your attention, right, from the first number to then the second number. So if we say 4 and add 5, what students need to do is first look at the 4, think about what 4 means, then look at what you need to do with it, adding, right, and then at the next number 5. So you kind of need to switch your attention and inhibit at the same time any information that is not relevant. So there's a lot of different processes and a lot of different ways in which mathematical development can go slightly wrong. And so I want to give you a few examples of whether that is different or the same across different groups with special educational needs. Oh, and a couple of people have mentioned, indeed, a home environment has an influence on mathematical development. And we also know that the school environment, or coming to school and attendance, of course, that these factors also play a role. Today, I won't have much time to talk about the home environment, but as Fliss knows, we're doing a number of studies that are looking at the home environment and the impact on mathematical abilities. And then, of course, there's also the school environment. It's also important, and apologies, this is it's not a real model. It's a schedule of a model that we're working on at the moment, is that all these abilities develop in tandem with one another in children, right? So when we think about what young children can do, these are pre-verbal children, they can pay attention, they can move around and develop their motor abilities, and their processing speed will be developing. But these things don't develop, in isolation, they develop in line with one another as well. So if you pay attention to something, you'll have better reaching abilities, you'll get better fine motor skills, etc. And of course, when we then think about slightly older children around the age of 2 to 3, we see that language is developing, but that also that their executive functioning abilities are developing and that their visuospatial abilities are developing. We know from child development that young children who have better motor abilities will develop better visuospatial abilities because they can move around a lot more and explore a lot more. So of course, they will develop these visuospatial abilities a lot more. And we also know that when children have better language abilities, they'll develop better symbolic mathematical abilities. So learning the digits and learning how to count will be easier when you already have language. So as you can see, there's lots of different arrows, meaning that these abilities all interact with each other over time. And so it's quite a messy thing. So you can start to also appreciate then that when a child's got problems with attention, for example, or when a child's got problem with motor abilities, this will have a knock-on effect over time on their mathematical abilities. And that when a child's got problem with language and communication, for example, this again will have a knock-on effect, not just on one of those abilities, but very likely on a number of those abilities. And that, of course, will have an impact when we're thinking about interventions or how we can support students who show mathematical learning difficulties. So what am I going to talk about today? I'm going to focus on, as I mentioned already, on 3 groups. So I'm going to look at autism, SLCN, and Down syndrome, and look at whether the difficulties we see in these groups are the same or different, and what that might mean in terms of ways forward. So when we look at, mathematical abilities in autism, there are a few studies that have been done, looking especially at the early years, preschool years, and a few at primary school age, that suggest that a number of autistic students have problems with maths specific abilities. So thinking about, they have problems with the approximate number sense. So this is what we call the ANS. However, when we look at all the studies together, these are kind of conclusions we can make. So when we look at the approximate number sense, we see that there are similar competences to typically developing children. That's what TD mentions. However, when we look at primary school age, we see that there are significant difficulties or impairments for autistic students. When we look at the number line, so this is again how you estimate, if we look at younger children, we see that they're similar. Yet when we look at studies that have looked at primary school age, we see that there's differences, that there are difficulties here. Again, when we look at counting, we see similar abilities. One of the things we know, though, is that there is a high variability in the mathematical performance of autistic individuals. And so this is one of the things that my PhD student wanted to look at. So Erica Ranzato has completed a study that looked at the following questions. So is the development of mathematical abilities in autism typical? Is it just delayed, or is it atypical? By atypical, we mean that it relates to other abilities than what we typically see in a typically developing population. How do domain-specific factors, so these are mathematical specific factors, such as your basic mathematical abilities, your counting abilities, your concept understanding, how do they compare between autistic children and typically developing individuals? And what are the domain-specific factors that explain the variability in the mathematical abilities of the autistic population? We know that that variability is there, but what drives that variability? Is it because some people on the autism spectrum have more language abilities? Is it because others have intellectual difficulties, whereas others do not? So in her study, she had a number of background measures, such as, Raven's progressive matrices. It's a nonverbal intelligence assessment. So we could see how the groups compare in terms of their intellectual abilities. She had a mathematical outcome that is a domain general numerical operation. Sorry, it's not domain general. It's a general mathematical outcome. She also looked at autism severity using the SRS, the social responsibility scales. And then she looked at a number of mathematical specific tasks, such as how good are they at number recognition? What do their verbal counting skills look like? How about their number line abilities? What about their approximate number sense accuracy, so their processing of magnitudes? And then she also looked at some domain general tasks that we know are predictive of mathematical outcomes. So as I mentioned already before, visuospatial abilities, which was measured by the pattern construction task, as well as short-term memory abilities and working memory abilities. The group size was not as large as you originally planned, but COVID didn't help with, this, because a lot of her tasks had to be completed face-to-face. So in the end, she managed to assess 24 students on the autism spectrum and 34 typically developing children. And as you can see, there was quite a wide age range. And this is because she was going to use that age, that spread of age in her analysis, which you'll see in a minute. And the groups are more or less matched for mental age, but there is a little bit of a gap. So, this is again a difficulty because of COVID. She was hoping to get some more of these autistic students in her sample. When we look at their mathematical outcomes, we see in the typically developing children, there is a large range, and that's because we had a large age range, right? So with most students having a raw score around 20 on the Wechsler's individual achievement test. When we look at those in the autism group, we see that was considerably lower, with a few students who were doing quite well in a similar range as the typically developing population, right? As you can see here, again, just reminding ourselves that the typically developing group was actually quite a bit younger, not significantly, but quite a bit younger than the autism group. And as you can see, the autism group was performing lower, significantly so compared to the typically developing population. However, it's important to look at this further. So if you look at the slide here on the left, you see that the red dots are all the individuals or the children with autistic individuals with their chronological age plotted along the bottom. So younger children are around here and older children are around here. And then this is their score. And when you plot their score, you see in the typically developing population, there's a nice relationship between chronological age and raw score. Basically, the older you are, the better you do on this assessment. That makes sense. Mathematical abilities improve with age. These children are learning. What we see in the autism group is that the line is flat. However, there seem to be two groups. There seems to be one group that is doing particularly well. And as you can see, there are some red dots along here, along the blue line. And there are some red dots here where students show that they're much lower. So they're performing much lower than their chronological age. And again, this shows the variability that we already knew existed within autism when it comes to mathematical development. This allows us then to kind of go and ask the question, well, what predicts their mathematical abilities? If it's not age, because there's no prediction for age, is there anything else that predicts mathematical abilities in autism in a better way? Yes, there is. And one of the things is they're Raven's colored progressive matrices. And that's a measure of overall intellectual abilities. And when we plot them against their overall intellectual abilities, you see that there's a line that is almost or in a similar way to the typically developing population, right? So in both groups, there's a significant relationship between their intellectual abilities and their mathematical abilities. Erica didn't find that there was a relationship with autism severity. So it's not autism severity that improves or that relates to mathematical outcomes. It literally is their intellectual abilities. She also then looked at, are there particular mathematical basic skills that relate to these outcomes? And she looked at the approximate number sense. So this is the ability to see where is more, which relates to where is measuring the number sense in a way. And again, in typically developing children, you find that there's a relationship between how good children are at saying where is more or less and their overall mathematical abilities. But as you can see from the green line, this was not the case for those with autism. When you look at number line abilities, this is a little bit the other way around, is that the more precise your number line, so that's why it's a negative correlation, the more precise your number line, the higher your maths scores. And we find this in the typically developing children as well as in the autistic group. And this is for the number line from 0 to 10, as well as the number line from 0 to 100. So what does that tell us about mathematical abilities in autism? Well, it shows us that we should be careful about predictions we're making when we have autistic students in the classroom. Because one of the things is that actually in autism, the chronological age of a child doesn't tell you a lot about what that child can do, especially in terms of mathematical abilities. Some children will do much better than their chronological age. Some children will perform much lower than their chronological age, right? But it doesn't relate, mathematical abilities does not relate to the child's or to the autism severity, right? What it does relate to is to their overall intellectual abilities. And it also relates, we also know that the ASD group scores lower on the ANS task and lower on the number line task. So in the students who are struggling with maths, so the autistic students that are struggling, they seem to not have a very good number sense or an understanding around how numbers relate to each other. And we also see that when we look at what predicts mathematical abilities in this group, in autistic students, we see that it's their number line knowledge as well as their intellectual abilities, so what we call mental age, their overall cognitive functioning. And this is useful to know, of course, not only in terms of what to expect from the student, but also in terms of how we can help the student. So autistic individuals will really benefit from number lines, for example, and getting some further training in terms of how numbers relate. What are large numbers? What are small numbers? Does this make sense, or are there any questions at this stage? Okay, then I'll move on. I am very happy to take some questions at the end. So then we looked at what about mathematical abilities in students with SLCN, so speech, language, and communication needs. And many of you may already know that this is a very diverse group of students that we're talking about, because this includes students who might have general language disorder, as well as students who might have developmental language disorder, or what we used to call SLI, specific learning impairment, as well as those with speech and sound disorders. So it's a wide group of students. When we talk about, what we know about mathematical development in this group of students is actually we don't know a lot. There haven't been many studies that looked at mathematical development in students who struggle with language development as well. So Chris Donlan, who was a colleague of mine at UCL in 2007, looked at what we used to call the SLI group, or what we now refer to as developmental language disorder, or DLD. And he included a sample of 48 primary school students with developmental language disorder. And he compared their mathematical abilities to a group of typically developing students that were matched for their language abilities, as well as another group of students that were matched for their age. And he used a range of tasks that assessed their language abilities as well as their mathematical abilities. So, for example, counting aloud, there was a task around calculations with simple additions and subtraction problems, as well as a place value task. So this is a task where students are shown two numbers. So it's, for example, here, so 1,892 and 1,792. And then students were asked to pick out which one was the biggest number, the greater number. And so when he then looked at the data, he showed that students with DLD performed significantly lower on all of the tasks. So when looking, for example, here at counting aloud, the students with SLI performed poorer, or with language difficulties, both groups performed lower. They performed lower on calculations, and they performed lower on multi-digit magnitude comparisons. So, to give you a little bit more qualitative data around this, so for example, 40% of the children with DLD, but only 4% of those with similar language abilities had problems to count to 20. So that's quite a significant problem when these primary school children who are about the age of 8 really struggled with counting to 20. But it's not just the counting that's the problem, but also their understanding of the place value principles. So understanding what are the units, the teens, and the hundreds and thousands, for example, compared to age controls. Kevin Durkin in 2013 looked at a much larger sample of students with developmental language disorder, and they were assessed at 2 different time points, so age 7 and then a year later. And again, they looked at lots of different measures of language abilities or psycholinguistic development in terms of their expressive and receptive language skills, also their IQ score, and then one particular assessment that is used within the British Ability Scales, which is often used by educational psychologists in the UK. And they did the basic number skills. The basic number skills subtest of the BAS, as we call it, the British Ability Scale, has a lot of different items in it. So one item is, for example, as you can see on the screen, a word problem that students have to solve, and they get visual support with it. They can use a paper or they can use their fingers to solve it. Other times they're shown digits and asked to say, what does the digit mean? What can you read out a digit? And in other times they're asked to solve mathematical problems. Okay. Basically, what Kevin Durkin found for the students with DLD is that they were on average 1 standard deviation below at both age points compared to their age-matched peers. So because of their language difficulties, students were performing a lot lower on the number skills task. And so although the students, because he assessed them at 2 time points, in terms of raw scores, the students with DLD were improving, but they were improving at a much lower rate than the typically developing students. And so what you see is that the gap between the students with DLD and those who are typically developing increases over time. And indeed, when you then look at, how much does language abilities explain variability in how much students are improving, you see that there's a significant amount of variance being explained, 19% at the first time point and 17% at a second time point. So if you could improve the language abilities of these children, you will improve a significant proportion of their mathematical abilities, but there's still a lot of other variance that is unexplained as well. But it might be also that the task seems to matter, right? Because when we think about the number skills task that is used in the study, it's a very language-based task, right? So there's these language problems that students have to solve, which then include mathematical ability. So the question is, are you measuring language abilities in these tasks, or are you measuring their mathematical abilities, right? And we can kind of think around it like, sometimes we say Jordan has 3 apples more than Charlie, Charlie has 6 apples more than Alex, Jordan has twice as many apples as Alex. How many apples does Charlie have? We're not going to solve that today. Or you can kind of ask problems, mathematical problems, more in a digit way, as we see here on the left-hand side. So this is what another of my PhD students, Helen Williams, did. So she looked at 13 students with SLCN. I know it's a small sample. Again, her research was significantly affected by COVID, and typically developing children. They were matched for their BPVS scores. For those of you who are familiar with it, not familiar with it, it's the British Picture Vocabulary Scale. It's a measure of vocabulary comprehension. Which is only, it's not, of course, a full language measure, but gives you an indication of the students' language abilities, and they were matched for that. But there was a wide range in both groups. And she used the White Rose Year 1 spring term arithmetic and reasoning assessment because they're very different. So in one of them, you've got in the reasoning assessment, you get kind of these word-like problems, whereas in the arithmetic task, it's much more, you know, they're focusing on the numbers and have fewer language demands. I won't say none, because of course there is still an instruction to be understood, but it's got fewer language demands. And indeed, what she found was that if you look at the total arithmetic score of the students, there weren't any differences between the two groups. The students didn't do particularly well, but, you know, again, this was during COVID times. But if we look at the reasoning assessment, there was a significant difference between the two groups. So it seems to suggest that students with speech and language and communication needs have particularly lower marks on a maths assessment task when that task really has higher language demands. So the type of task seems to matter. And also it shows the importance of the training for mathematical language, especially, you know, thinking about, I've got a slide here, thinking about, you know, when we think about mathematical language, there's a lot of concepts that actually we implicitly use without maybe teaching it explicitly, but for students who've got speech and language and communication needs, this really matters. So understanding, for example, 4 more left, 2 plates for us, how many words like minus, add, in addition, moreover, in sum. These are all, this is all terminology that is mathematical in a way, or are things that we use in mathematical lessons that students may not necessarily understand. Think, for example, about there's a table, and that could be a table to eat from, or there could be a table, but that table looks very different if we're talking about maths, or a table where that contains data, for example. So it's important to assess for students with specific educational needs whether they've really understood all the language that is being used and all the mathematical concepts that we're using, and to teach that explicitly. I want to, before finishing, look at one more group, and that's students with Down syndrome. So why do I look at Down syndrome? As you may know, Down syndrome is a genetic condition that occurs 1 in 800 live births, so it's quite common. And students with Down syndrome often have an average IQ score around 50. So many of them have intellectual disabilities, and they also have expressive language difficulties. So again, we can see the speech, language, and communication needs in this. In our studies, we often compare them to individuals with Williams syndrome, which is a rare genetic condition that occurs about 1 in 20,000 live births. But they have very similar intellectual disabilities to those with Down syndrome. So again, their average IQ is around 50. There is a spread of scores, just like with individuals with Down syndrome, but very different cognitive profiles. So whereas in Down syndrome, we might see problems with expressive language and short-term memory, what we see in individuals with Williams syndrome, those are a strength. Whereas in individuals with Williams syndrome, we see specific difficulties with visuospatial abilities, which, again, if we look at our students with Down syndrome, we see that visuospatial abilities are a strength. So you get this very nice divide between what is a strength in one group is a difficulty in the other group, and vice versa. And that allows us to kind of look at how important are these domain general abilities, like visuospatial abilities, like language abilities, for mathematical development. So a lot of my studies have looked at mathematical abilities in Down syndrome and in Williams syndrome. When we look at mathematical abilities in Down syndrome, what we see is that they have problems with subitizing, they have delayed counting skills, which we do know relates to their language delay, and they have problems with comparing numbers. When we look at those with Williams syndrome, we see that they have problems with large quantity discrimination, so this is their approximate number sense, that again, they have problems with digit comparison, but although they're very good at counting, and they can count, if you ask them count as high as you can, they're not different from typically developing children, yet they really have difficulty with understanding what counting is for. So what we call cardinality. So when you ask them to count the items in a set, they don't understand that the last number you've counted is how many items there are within that particular set. And they have problems with symbolic representation, so recognizing numbers and understanding the units and teens and hundreds. So what we did in one of our studies is we looked at individuals with Williams syndrome across a very wide age span, and that was done on purpose. I mean, 8 to 51 is because we were interested in mathematical development to see if there's any changes over time. And we did the same for those with Down syndrome. And then we had a typically developing mental age match group. So of course, they're much narrower in their age range. And we looked again at their general intelligence using the Raven's matrices, visuospatial abilities, their non-symbolic abilities using approximate number sense, guessing where is more, and then symbolic abilities, we asked them to count and gave them a digit recognition task, as well as then again this numerical operations task from Wyatt that Erica also used in her studies when she looked at mathematical development in autism. And what did we find? And don't worry about this graph, I'll explain to you. So at the bottom, you've got, again, the Raven's colored progressive matrices raw score. And then in the other axis, we have the Wyatt raw score. And what you see here is in typically developing children, the straight line, you see a nice, again, relationship, between their intellectual abilities and their mathematical abilities. Basically, the smarter the child, or the better their mathematical abilities. We see the same things in those with Down syndrome, and also to a certain extent those with Williams syndrome, but there is a larger variability. So we know that in all groups, mathematical abilities relate to their mental age or their overall intellectual capacity. What about their number line task? Well, what we found was that there were no differences between the three groups in terms of their number line performance because they were matched on intellectual abilities, right? Oh, these were the wrongs. Yeah, but what we do see is when we look at what predicts this ability, what we see nicely in Down syndrome is it relates to their visuospatial abilities. So the better your visuospatial abilities, which we know is a strength in students with Down syndrome, the better their number line abilities. Again, a negative correlation because with number line, the better the score means the lower your discrepancy between the actual number and where the person put it, right? So there's a less of a default there. In Williams syndrome, we don't see that. We see that actually their number line abilities are predicted by their number familiarity, so how good they are with their number knowledge, but not with their visuospatial abilities. And that was for the 0 to 10 scale, and to some extent to the 1 in 100 as well, except for those students with Down syndrome, it wasn't quite significant because they found this task very difficult. When it comes to their approximate number sense task, so this is the ability to guess or to estimate where is more, at red dots or blue dots. What we see here again is that in the blue line is the typically developing children, the red line is the Down syndrome children, and the green line is the Williams syndrome. As you see, in typically developing children and in children with Down syndrome, there is no relationship between their mathematical abilities and how good they are in predicting where is more. And that makes sense because these people are a lot older than studies that have looked at magnitude development. So we know that magnitude development is very important for preschoolers, right? But once students start to learn the symbolic system and the digits, they're no longer going to rely on this magnitude ability. They're going to use numbers to solve problems, right? And not just their estimation to solve problems. But what we do see that is that in individuals with Williams syndrome, this ability to understand magnitudes is still a predictor for their mathematical abilities. And it's because they're so poor on this task that it remains a predictor on their mathematical outcomes. Okay, so what does this all mean? What's my message to you? There's a couple of them. One is that mathematical development is complex. And so we really need to think about what there are different domain general and different domain specific abilities that will predict mathematical abilities across these different groups. And it's really important in order to help students with mathematical development to think, why does this particular student have problems with maths? And what we see in our studies that it might be for very different reasons. So in students with Williams syndrome, we know that their number familiarity is a predictor for their mathematical outcomes and their approximate number senses. We know in students with Down syndrome, they're poor at maths, but their visuospatial abilities seem to be a predictor. So the better their visuospatial abilities, the better they'll be at maths. We know in autism, it seems to relate to number line abilities, whereas in speech, cognition, and language needs students, it relates to their language abilities. And so this seems to suggest that we might want to think around, in order to help these students, we might need to help them in different ways. So we know for autistic individuals, we know that training them on number line abilities will improve their mathematical abilities. We know that in speech, cognition, and language needs students, we might need to think about what the task looks like and train them on the language and the concept of the mathematical the mathematical language. For those with Williams syndrome, it seems to be that we need to go back to basics and really training on these magnitude comparisons and their number familiarities. And that for students with Down syndrome, it might be that their visuospatial abilities need to be trained. And again, what that means is that they will benefit not only from number lines, from wider training as well, but number lines will definitely help them as well as concrete materials. So hopefully I've shown in our studies that what it shows across these different studies, that different interventions will work differently for these different children. One of the things I haven't been able to focus on today is also that we see different age differences as well, so that what I've spoken about today works for preschoolers and primary schools children, but that as children grow older, there might be other things that we might need to do because that gap becomes wider. We don't yet know very well what works for different groups with SEND when it comes to maths. And that's why we're doing a new study at the moment that is funded by the Nuffield Foundation, where we're synthesizing all of the evidence. So that means all of the published research that is out there in terms of what works for different students with SEND aged 4 to 25. We found 56,000 studies that we had to go through. We've whittled it now down to 530 studies that make our inclusion criteria, and we hope to finish this by March. So this means doing data extraction that will allow us then to do a meta-analysis. So basically that will allow us to see which interventions, these are all tier 2 and tier 3 types of interventions, work best, so they create the largest effect sizes. And how that then relates to the different phases of education, preschool, primary, secondary, post-16, and within different contexts. So we're also looking at, was the study done with students from special versus students from mainstream schools? And we're looking in this study not only at maths, so maths is one of our educational outcomes, but we're also looking at this in terms of writing, reading, science, and general attainment. So hopefully that will then tell us a little bit more. We'll make a toolkit based on these studies. That can hopefully help you. As part of that study, we're still looking for teachers, SENCO, school leaders, and educational psychologists and other professionals to take part in a 30-minute online interview at a time that's convenient to you, because we would really like your input in terms of how you find out, in terms of your tier 2 and tier 3 types of interventions, how they're implemented in the classroom. But we also, and more importantly, would like some feedback on the toolkits that we'd like to create, because we want to make sure that whatever toolkit we create will be helpful to you as professionals. So if you'd like to participate in one of those interviews, then please use the QR code or use the link here, or I can also still put in a chat later on if you're interested in that. But thank you very much for listening, and I'm very happy to answer any questions.